back to our third topics for this course, the circuit analysis 1 by อาจารย์ปัทมาพร at Kasetsart University, Bangkok, Thailand. This third topics will be on Kirchhoff's law. Okay, there you go. This is how we spell it, Kirchhoff's law. Well, it was introduced. The laws were introduced by a German physicist, Gustav Robert Kirchhoff. Okay, so there are two laws associated with Kirchhoff's. These are the Kirchhoff current law, KCL, and Kirchhoff's voltage law, KVL. So from now on, you will hear me saying KVL, KCL, apply KVL, apply KCL. Okay, which you have to associate with the Kirchhoff voltage law, KVL, and KCL for Kirchhoff's current law. Okay, well, the two laws, let's start with Kirchhoff's current law first. Okay, KCL. Okay, before I begin with this law, we have to define a word known as a node. A node. Okay, a node or a junction. A node or a junction. Okay, is a point of connection between two or more so-called branches. Okay, so if you have anything that has an element in it, either going to be resistors, inductor, water source, we call it a branch. Okay, so this is one branch, this could be another branch, and if we connect them together at one point, okay, then this is a node. Okay, it could be two branches or three branches. You have another resistor, so this is a node. Okay, well, for the KCL, the Kirchhoff current law, it stated that the algebraic sum, KCL state that the algebraic sum of currents entering any node is 0. Okay, right? So what does it mean by the algebraic sum? The word algebraic sums means that it can be positive or negative values. Okay, and you add them up. Okay, so therefore, let's have a look what it is. So in this picture, okay, in this figure right here, there are three nodes. Okay, there are three nodes. So this branch here and this branch here connect together. This is one node. This branch and this branch, this is another node connected at another node, and this is the third node. It's this branch and this branch connected together, but of course not, have with an extended wire. Okay, but it's still the same node. So there are three nodes here. Okay, just to clarify what nodes are. So another example in this case, okay, there's also three nodes here. Okay, so this is one node right here. So all this connected, this branch, so 4 branches. This is another node, and this branch and this branch connect together, so this is another node. Many people will miss this one and say there's only 2 nodes, but there are actually 3 nodes. Okay, it can also be easily seen when we draw it like this. Okay, that this is one big node right here, this is another node, this another node. So these two figures are the same figures. Okay, the same circuits. Okay, so that's node. Now, to write down KCL, we must have the current going in and out of the node. Okay, for me, to make it easier to understand, I always tell my students, imagine that the node that you are going to write a KCL is your pocket. Okay, your pocket, and the current is represent as your money. So money flowing in and out of your pocket. So if the current's entering your node, you can think of it as money, flowing into your pocket, and that's give you a very good feeling. So it's positive feeling. So you give it a positive values in front. Okay, the positive sign in front. But if the current's leaving the node, leaving the node. Okay, you can think of it as your money flying out of your pocket, and not very nice. So it's negative feeling. So put in a negative values, negative sign in front of the current values. So therefore, if let's say this picture, okay, I have a node A, and I have current 6 branches with 6 current going in and out of that node A. Okay, well, let's look at each current. Okay, so I1, right? I1 flows into the node. So happy feeling, right? Like money flowing into your pocket. So positive I1, right? Positive I1, right? So I1. I2 also entering, so positive I2. Okay, I3 also entering, so positive I3. Then I4, but I4, the current's leaving the node, so like money flying out, so negative feeling, so minus I4. I5 also leaving, the current's leaving the node, so minus I5 and minus I6. So that's all the currents going in and out the node. So all this must be equal to 0. Okay, so this is KCL. I always write it like this, KCL at node A. So this, okay. If you don't like the negative sign, right, it would be I1 plus I2 plus I3, right? Change side, so become I equal to I4 plus I5 plus I6. Okay, and you can realize that, oh, I1 plus I2 plus I3 is the sum, right? Is the sum of the current going into the node, and equal to the sum of the current leaving the node, out of the node, leaving the node. So this is another way of saying the Kirchhoff's current law. Okay, sum of the current going to a node is equal to the sum of the currents leaving the node. Okay, it's the same thing. So this is KCL. So simple, see, right? So for simple questions, okay, so you can look at this example. The question asks what's I total, right? So if you look at node A, right, I total comes right out of the positive side of the source, flow into node A, then it's split right into I1, I2, and I3. Okay, if I write KCL at node A, it would be, well, I total is positive going in, right? I1 is leaving, so minus I1. I2 is leaving the node A, minus I2, and I3 is also leaving the node A, right? So equal to 0. So therefore, I total equal to I1 plus I2 plus I3. How about if I write it from the so-called node B? So if I write KCL at node B, right? Oh, this time I1's entering, so I1 positive I1. I2 also entering, so positive I2. And I3 also entering node B, so positive I3, equal to the I total leaving node B, so minus I total equal to 0. So therefore, you get I1 plus I2 plus I3 equal to I total. So same answer, right? So this is KCL, just add and subtract. Okay. So for example, this example, what's I total, right? If you think of it this is as a node, right? There's a node right here, right? So I total entering this node, positive, minus 5 milliamp because 5 milliamps leaving the node, and minus 12 milliamp also because leaving the node, equal to 0. So I total equal to 12 milliamp plus 5 milliamps equal to 17 milliamps. Okay, or this one, find IR2, which is this one, IR2, right? So what is IR2? So you see this node right here, there's a node right here, okay? Actually, the whole node is right here, okay, right? But just for you to see it more, to apply more correctly, let's put it right here, node A. So KCL at node A, okay. Well, 100 milliamps is entering, so positive 100 milliamps. 30 milliamp is leaving, so minus 30 milliamp. minus IR2 because IR2 is also leaving node A, and minus 20 milliamps, okay, equal to 0. Don't forget to equal 0 sign. So and then therefore you would get IR2 equal to 100 milliamps minus 30 minus 20 milliamps. So therefore IR2 equal to 50 milliamps. Okay, so do you see the point of this? Okay, well, you can try to find this problem by yourself. Okay, write it down. Okay, 5 milliamps come out from the source, split into 1.5 milliamp or 1.5 amps, 1 amps, and you have to find IR3 and I1. Okay, right? So, how do you do this? So, KCL. Let's look at KCL. Okay, this is you have to be able to identify the node. Okay, so you identify this node right here. This is a node right here, right? So 5 amps going into the node, positive. 1.5 is leaving, so minus 1.5. Minus 1, right? Minus 1. Okay, minus 1. Minus IR3 equal to 0. So therefore, you get IR3 equal to 5 minus 1.5 minus 1, right? Okay, and you get IR3 equal to, right, IR3 or I1, or IR3, right, IR3 first, right? So your IR3 is 2.5 amps, okay, 2.5 amps. You want to find I1. Well, if you look at simply at this node right here, I1 entering this node right here, right, node Y right here, okay, so you can write I1 is entering, right, minus 1 amp minus IR3, which is 2.5 equal to 0. So I1 equal to 2.5 plus 1 equal to 3.5 amps. Okay, so you can find it, the value of the current using simply KCL. Okay, KCL. Next one. Okay, next one is KVL, Kirchhoff voltage law. Okay, well, Kirchhoff voltage law, KVL states that the algebraic sum of all the voltages around a closed path or a loop is 0. Okay, so we have to identify what a loop is. Okay, so a loop is any closed path through a circuit in which no node is encountered more than once. Okay, so therefore, so there's a word loop. Okay, another, I'm going to tell you there was a loop. Later on you will hear loop or mesh. Okay, let me define it right here. Okay, so let's say that I have an example. Maybe you can see an example more clearly. Say I have this picture, this figures. Okay, so a loop, okay, is a closed path through a circuit in which no node is encountered twice. Okay, so this is a node, this is a node, right? This is a node and this is a node. Okay, so therefore in this picture, the purple color here, this picture, there are 3 loops. So there's this one loop, L1, this one is L2, and there is this loop, L3. So these are loops. So you can see that as you go along all the lines that I draw, L1, L2, and 3, it doesn't encounter the node twice. Okay. Now the word mesh. Okay. Mesh is a loop that does not have any loop inside. Okay. A mesh, okay, is a loop that does not have any loop inside. So therefore in this picture, right, we have L1, L2 and L3 These are loops. But only two meshes. So only L1 and L2 are meshes. Okay. L3 is not a mesh because L3 has L1 and L2 inside. So this is the definition of loop and mesh. Okay. So now go back to KVL. KVL states that the algebraic sum of all voltages around a closed path or loop is 0. Okay. So therefore, if we look at these figures right here, in the black figures here, 2.8, okay, we have a loop, right? We have a loop, and this is the current. Let's give it a name, I1 as a current. Okay, current leaves the source, positive side of the source Vs, pass through the first resistor, result in a voltage drop, positive, negative, right? Current enter the positive, okay, of the voltage drop V1, V2, V3, and V4. KVL, Kirchhoff voltage law. Remember voltage, so you're going to add voltage. KCL, current. Add that for KCL, we add current. Okay. So now KVL, we're going to add the voltage around the loop. Okay. So imagine that you are current. You're current and you're walking. Okay. You're walking around loop in the direction of the current that you have drawn, I1. So in this case, if I start walking from here in the same direction as I1's walking, right? Whatever the sign you encounter first, you write it down. So you walk here, you see, what do you see? You see minus Vs, minus sign, right? So minus Vs. Go on, keep going, you see positive V1. So positive V1 plus V1. Go on, you see positive V2, you see the sign positive first of V2, so positive plus V2. See positive V3 plus V3, see positive V4 plus V4. Then when you come back to the same where you started, it's set it equal to 0. This is KVL. So I normally would write it like this, KVL of loop L1, loop I1. Okay, so if you don't like the minus sign here, change side. So you would have Vs equal to V1 plus V2 plus V3 plus V4. Or in another word, we can say that KVL stated that the sum, this is the sum of the voltage drop, okay, around the loop would be equal to the source voltage of the loop. So this is another way of saying KVL. Okay. See, the sum of all the voltage drops around a single closed loop in a circuit is equal to the total source voltage in that loop. This is another statement for KVL. Okay. So therefore, for example, we have a loop here, and we want to find Vs, right? So there's a current direction given like this I. So I'm write KVL for this loop I, right? So if I start walking from here, right, go in the same direction as the current. See the positive sign first, 7, positive 7. So it's important for me, and also for those who new students, new knowledge here. It's always a best practice to write down the polarity, positive and negative, of your voltage drop, so you won't get confused or make a mistake. So positive 7, you walk here, see positive 3, right, plus 3. Walk through here, see positive 2 of this R here, the voltage drop, then positive 10, then goes here, see minus sign first, minus Vs equal to 0. So therefore Vs equal to 20 volt. Okay, so this is KVL. Just simply adding, and subtracting. Now how about this one here, this example? Okay, so write down KVL for this loop I1, let's say I1. So if I'm going to walk from this point onwards, right? So I walk from here, see negative sign, minus Vs, Then go up here, see positive 10 volt, positive 5, right? Good. Positive 2. And then this is positive 7 equal to 0. So therefore your Vs is equal to 24 volt. So therefore, especially when you have more than one sources, sometimes you may get confused. Okay, so it's safe to write down the KVL to make sure you get the correct answers. Okay, whether you're going to have to, how you're going to combine the sources together. Okay, right, so this is another example, right? You can try. So apply KVL, start walking from here, so positive 7, positive 3, plus V3, see minus here, minus 5, and then this one also minus 10, so minus 10. So therefore V3 is 5 volt. This is how you apply KVL to find a voltage in a loop. Okay. So this is pretty much it, Kirchhoff's law. Okay. The next topic I want to introduce to you is why do we call things parallel circuit? Okay, parallel circuit. What is the definition of parallel? What is the definition of parallel? Okay. So parallel, when things are connected in parallel, it means that they have the same node. Branches are said to be connected in parallel when they have the same nodes on both ends. On both ends. Okay, on both ends. So therefore, this picture, okay, all of the elements are all in parallel because we see that this is pretty much the same node on the top here and also at the bottom on both ends. The top ends, right, and the bottom ends like this, so the same node. If you to draw this, you can draw it like this also, right? If you want to see it more like, okay, it's a node, it's the same thing. How many are there? 4 are. It's like this. So this is Vs, this is V1, this is V2, this is V3, this is V4. Okay. So if you use a voltmeter to measure the voltage across from point A and point B, they would all be the same. They would read the same for all the branches. So therefore, we would have Vs, the voltage of Vs equal to V1, equal to V2, equal to V3, and equal to V4. Okay. So all the voltage drops in the resistors are equal to the source voltage. Okay, so parallel, definition of parallel. Okay, something in parallel. So these are all parallel connections. So these two resistors are connected in parallel because this is the same node here and the same node here. Okay, this is also in parallel. These two resistors in parallel because this is the same node. Okay, the wire, it's just like we consider the wire has no voltage drop, so it could be shortened along. It's still the same point, connect the same point. So this is another node right here. So AB, like this. Okay, these also resistor also connect in parallel because this is the same node and this is the same node. Okay, this is also in parallel. Okay, this is the node on the, let's say, the top end of the resistor, two resistor, and this is the same node. This is another node. So this is A, this is B. The other end of the resistor is connected at the same point. Okay, so they are all in parallel. Okay. Now let's look at if I connected current sources in parallel. Okay. Please remember that when you have current sources connect in parallel, you can add them up. Okay, you can add them up. Okay, algebraically sum them together, and please represent them as one source only. So, for example, this case. Okay, if you're not so sure whether it's going to be 1 amp minus 2 amp, which current direction is going to be positive, which current direction is going to be negative, apply KCL. Okay, so you think of it as this is one node right here, right? This is a node. This is a node right here, same node. Okay, IT is leaving like this. Okay, want to find IT. Well, you can see that 1 amp is entering, so plus 1. 2 amps also entering, so plus 2. These 2 amps also entering, plus 2, but IT is leaving the node, so minus IT equal to 0. So IT equal to 5 amps. And you can represent it as simply, right, 5 amps, like this. You can combine this together and represent it as just one current source with that final values. Okay, about this one here, same thing, right? Okay, I total is leaving the node like this, but then you have I1 amp leaving the node, so minus 1, right? 2 entering, so plus 2, and I total is leaving node equal to 0. So therefore, I total equal to 3 amps. So therefore, we can write it as this is 3 amps and I total. Combine these together to get this. Okay, but you have to make sure, which current direction I meant to be a positive, right? Because this is, I say positive going in like this. So when the answer is 3, it means that I have to keep it consistent that going in is positive 3. Okay, so therefore, this is when you have a current source connected in parallel, okay, or right here, okay. What do you want to find VE, right? Well, V Ohm's law, VE would be equal to the current across RE, right? IR times RE. So VE is equal to, well, this is going to be 1K ohms. Well, what's IRE? The I that going through IRE like this, right? You have to see that, oh, it comes out from this node right here. So therefore, I can write KCL, right? So 10 milliamps going in plus 10 milliamps going into that node, and IRE is leaving that node. If I say this is node A, so KCL at A is this, equal to 0. So IRE is 20 milliamps. So therefore, insert 20 milliamps here, so you get 20 volt as the answer for the voltage. Okay, so now we combination of KCL and Ohm's law together to solve of simple problems. Okay. Now, next, well, this one, right? When you have a source connected in parallel, we add them together. What about if we have resistors connected in parallel? What can we conclude from that? Can we combine them together? What would be the formulas? Okay, so therefore, so as you can see, we have R1, R2, and R3, and Rn. You can go on forever, but they are connected in so-called parallel, because this is node A, they connect together, and the other end, node B, they connect together. Okay, so, well, we can write, well, since they have different current, right, from each branches, we can think that we can write down KCL. So write down KCL at node A. So KCL at node A, right? I total going in minus I1, because I1 is leaving, everything is leaving, so minus I1, minus I2, minus I3, minus IN, okay, to the very end. Or, change it to another side, so you get all the current going in equal to current leaving the node. So I total equal to I1 plus I2 plus I3 plus IN. Okay. Now, well, we want to combine our resistors together when we want to know what would happen, when they're in parallel, and we want to combine all the R's together. Okay, but right now we have already the current form, so you have to change it somehow to a formula that consists R, the resistor. So the only thing is Ohm's law, right? I equal to V over R, right? I equal to V over R from Ohm's law. So therefore, I total, well, I total is a current, the total current that has to feed all R1, all the R's that's connected to it. And it, the source itself, that push all these electrons going to from Vs. So therefore, I total is Vs over R total. So this is your Vs, or your Is, sorry, your Is. Okay, I total, sorry. I total, I put down I total. Okay. Now I1, of course, I1 would be the voltage drop across the R1, which is V1 over R1. So this is I1, right? This is I2. This is I3. IN. So I2 is V drop across R2, V2 over R2. So we get that. So we got all this, right? But we just define that the voltage are equals when things are connected in parallel. So that means your Vs, V1, V2, V3 are equal. So when they're equal, we can sort of like, which is equal to Vs, right? So V1, V2, V3 is equal to Vs. So you get it into this form, and we can cancel Vs like this. So you end up with 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. Okay, right? So therefore, if you want to find R total when you combined resistors that are connected in parallel, you have these general formulas. Or if you take the reciprocal of it, right, R total would become 1 over R1 plus 1 over R2 plus 1 over R3. So this is a total resistance when you connected them in parallel. If you want to make it your life, I don't know if it's easier or not, okay, you can use term conductance also, because G is equal to 1 over R. So therefore, G total is equal to 1 over R total equal to G1, G2, G3. Okay, but somehow I always work with R, not G. Okay. So this is the formula that you all, most of the Thai students would know, okay, from high school. Well, there's two special cases that you may want to use it. If you know it, it makes you how you solve your problem faster. If you have two resistors in parallel, R1 and R2, right? And you want to find R total. You want to combine the R1 and R2 together since they are connected in parallel. Okay, so you can do this math, right? It will 1 over R1 plus 1 over R2, which is of course equal to 1 over, R1, R2, R2 plus R1, right? So therefore, when you flipped it, take reciprocal, it becomes this formula. So your R total is R1 times R2 over R1 plus R2. This is another formula that many of the Thai students would already know. Okay, so I just want to prove it that this is how you get this fast formulas when you have two R's connected in parallel. If you have many number of resistors, n number of resistors, but they are all equal values, right? So this would be the formula. Is that value of the resistor divided by the number of resistors that connect in parallel. So for example, if you have 3 resistors in parallel and each is 9 ohms, okay, then if you combine them together, okay, this become, right, if this is A, this is point B, this is A, this is point B, you combine them together, this become R, which is R value, which is 9, over number of resistors that connected in parallel. So there are 3 of them. So therefore, you would have 3 ohms when you combine them together like this. Okay, so it just make your life easier, when you do your problems. You don't have to go through all the formulas and use a calculator. Okay, so this is your so-called things about that brought about from KCL, right? So now next one I'm going to do KV. Let's see, KVL. Where is it? Okay. Let's go back to KVL. Okay. Now I want to define when things are connected in series. Okay, series circuit. Okay. So how do you know when elements are connected in series? We know that elements are connected in parallel when they have the same voltage, they have the same nodes at the top and the bottom ends. Okay, so for something connected in series, the definition is that, okay, currents that pass through those elements is the same. is the same. Okay, elements are connected in series when current passing through the element is the same values. So therefore, see, most of the time you know that, oh, okay, well, they're gonna connect, this is series connections. How do you know? Well, it's because, see, the definition is if you have a current flowing, right, flowing through this source, out of the source, through here, the current go through the first R, second R, third R, and come back, right? So the same current going through them. So these 4 elements are connected in series. Okay. Now, if you have voltage sources connected in series, we can also combine them together. We combine them together. Okay. So for example, this case right here, we want to find VAB. So VAB, as I said before, on the first topics, first lectures, A, I would take it as positive, B as negative. So this is VAB. Right? When you use your voltmeter, you know, the black leads go to point A and the red leads go to the point B. Okay. So to make sure that you get it correct, please use KVL. KVL. Okay. So KVL. So therefore, let's see, if you imagine that there's a line connected like this, right? So I'm going to walk, can I walk? You know, imagine this is like a loop, right? So I'm going to go from here and go like this. Okay, so KVL. So I see positive 1.5, right? Positive 1.5 here, right? Come here, I see negative VAB. Then finish, so it's equal to 0. Set it equal to 0. So therefore, VAB is equal to 1.5 plus 1.5 equal to 3.0 volt. See, like that. Okay. If you use KVL, you shouldn't get wrong answers. Okay. Right. Same here. Okay. If you imagine that, well, right, this is VAB plus minus VAB, right? 2 points. I'm going to walk it through like this. Okay, so KVL is, well, I see positive here, positive 1.5, positive 1.5, oh, same thing, positive 1.5, and then negative VAB equal to 0. So VAB equal to 4.5 volt. Okay. Sometimes if when you have a good grasp of it, you can just think of it as, hey, I can just write VAB. I don't have to set it equal to 0 all the time. I can look at VAB. If I want to write what VAB equal to, I just go VAB equal to, and then equal, whatever this right here is would be when I walk from point A to point B. Okay, so let's see. So VAB equal, right? Whatever I'm going to fill out, I'm going to walk from A to B. So point A here, I walk here and see positive 1.5. I see positive, another positive 1.5, and I see positive 1.5. So I get 4.5 volt. Okay. So how about this one, right? Maybe this one here. Okay. Right. So VAB, right? So VAB equal to, I'm going to walk from A to B. So I see negative 1.5 here, see positive 1.5, and then see negative 1.5. So therefore, VAB equal to minus 1.5 volt. Okay, do you see it? So this one I can do it like this, right? Since I write down, so this, it could be, well, VAB, I write like this, right? Because I said A is positive, so AB, right? But my answer is minus 1.5. So this is minus 1.5 volt. I have to write like this. Or if I don't like to write down minus 1.5, this is the same thing. I can write it as, but I have to flip, right? A and B. 1.5 is VAB. That means my VBA is positive 1.5. So it will be, if I write out VB, A, right, like this, B positive, A negative, this is 1.5 volt. So this is the same thing. Okay, you combine them together. You can, write just as a one source. Okay. Now, what about total resistance? As a source, I can combine them together, right? What about the resistors? If I have resistors connected in series, what would happen? Okay, so look at this loop right here. So we have a loop, so we have KVL. So KVL for this loop, okay, is, well, minus Vs, right? Current goes out here, positive, negative V1, positive, negative V2, positive, negative V3, positive, negative V4. So plus V1 plus V2 plus V3 plus V4 all equal to Vs equal to V1 plus V2 plus V3 plus V4. Okay. Well, Ohm's law, we're going to find R total, right? R total resistance of this circuit, or this R1, R2, and R3, and R4. If they connect in series, what would be the value if I want to combine them together? Well, V equal to IR, so therefore, I is the same I, right? So IR total, right? Because Vs here has to provide connected to all the R's in the circuit, equal to V1 would be I times R1 plus I times R2 plus I times R3 plus I times R4, because there's the same current going through them. So since they are the same value, so you can strike out the current. So your answer is, your R total turn out to be R1 plus R2 plus R3 plus R4. Okay, so this is the formula that we all know by heart. Okay, the total resistance, when we have resistors connected in series, you just add them up. Okay. So therefore, in this case, the one, oops, hold on. So in this case, right, this picture right here, I can write it as, well, I have Vs and all the R's combined together. So this R total becomes R1 plus R2 plus R3 plus R4. Same I going through. So I can combine the R's together also. Okay. But of course, you have to, when you later on you solve the problem, sometimes you can combine only these two, but the other one you cannot, because you may alter the problems. So we will see later on. Okay. But anyway, but this is the total resistance. So therefore, in this case, okay, if you want to find the current I, right? Well, it would be, well, I would be the current going through all the R's and the voltage source. Okay, since we know the voltage source value, so I is equal to the voltage source value V over, well, the source has connected to all the R's, R total, so R total, right? And we know that, well, the same current passing through 3 to 5 ohms right here, they're connected in series, so R total is equal to the sum of all of them, right? So 15 ohms. So divide by 15 ohms, you get the answer for I. Okay. So this is how we make use of Kirchhoff voltage law and Ohm's law. So let's look at this one. Let's find I also. So I have, according to the current that leaving this positive side of the source, right, going clockwise directions, I going passing through, there's pass through also 5 volt right here, pass through 10 ohms, so I give it positive sign here, right? Current go positive, positive, and positive, voltage drops. So if I run KVL, right, walking down from, let's walk from, starting from here. So you see negative minus 3, so minus 3, see positive, right, positive 5, see positive voltage drop across 10, so this is V10, okay, and this is V12, and this is V8, okay, V8 ohms. So see positive, voltage drop across 12, voltage drop across 8 ohms, set equal to 0. This is KVL. Well, we want to find current I. They are in voltage, VV. We need to change it to I. You have to find a relationship, a formula that in your head that's somehow relating this V across 10 ohms and current going through the 10 ohms. So the only thing is, of course, Ohm's law, right? So V equal to IR. So you would substitute V across 10 ohm as 10 times I, 12 ohm voltage drop across 12 ohm as 12 ohms times I, and 8 ohms is the voltage drop across 8 ohm is 8 times I. So you will get, when you do the math, right, it will become minus 2 over 30. So you can see there is a minus sign here. The answer come out to be minus sign. So that means that the current that in this direction that we have specified, we have assigned, the value I is minus 2 over 30 amps. So actually, in real life, if you connected this circuit, the current actually go in the opposite direction counterclockwise with the values of 2 over 30 amps. 230, okay? So therefore, the negative sign give the directions. If it's positive, it means that it's the same direction as what you have assigned it when you solve the problem, when you are solving the problems. If the answer turns out to be negative, it means that whatever you have assigned, the current actually goes in the opposite directions. Okay, so this is what it is for the Kirchhoff voltage law and Kirchhoff current law. This is the topic. Thank you very much. I see you in the next topics.